Diminishing hops for minimum vertex cover. You may be already wondering what is this new term in the context of the minimum vertex cover problem. And obviously the image on your screens does not paint any picture whatsoever, let alone a technical one. Hence, let me start by using an analogy that will paint at least half a picture on diminishing hops even before I actually introduce the concept. This idea is heavily inspired by the use of augmenting paths for maximum matching. And specifically, there are three words in this sentence that got me really fixated: augmenting, paths, and the word maximum. So using this sentence, we are moving towards having diminishing hops for minimum vertex cover. And given that our aim is to minimize the size of the vertex cover that we have, instead of augmenting an existing vertex cover that may be given to us, we want to diminish or decrease its size. And we do so by hopping around in the graph instead of following a set path. On a more formal terms, the Blossom algorithm relies heavily on Burge's lemma, which is to say that given a graph G and a matching M is the maximum matching if and only if there is no M augmenting path in graph G. Analogously, our aim is to prove the following lemma. Given a graph G, a representable R, and a vertex cover S derived using R, S is the minimum size vertex cover derivable from the represents table if and only if there is no S diminishing hop in table R. Now, all this being said, what is exactly diminishing hop? So let us understand this concept using an example. And for the example, I'll fast forward the example, and instead of showing you the graph that we start with, we have this already populated representation table after implementing our proposed algorithm. And just to recollect your memory on what a representation table is, consider this subgraph of a larger graph that we are probably working with. And the algorithm that we are proposing, during the maximal matching phase of the algorithm, let us assume that it picks edge that connects vertices 10 and 11. Consequently, vertex 10 becomes endpoint 1 and vertex 11 becomes endpoint 2, and the vertices that are connected to each of these endpoints fall within the represents table. So that means that endpoint 10 represents vertices 11 and 12, and endpoint 11 represents vertices 10 and 7. So this is how the representation table is populated, and we already have this pre-populated table given to us, and we also have a set of vertices which forms a vertex cover. Now we know that at least one of the endpoints in each row need to be in the vertex cover, otherwise it won't remain a vertex cover. Hence, we identify rows wherein both of its endpoints are part of the vertex cover, which in other words means both of the endpoints are already frozen. In that case, what we would want to do is we might want to remove one of the endpoints and consequently assess how many endpoints from the representation table need to be removed or frozen to eventually figure out if it is possible to diminish the size of the representation table or not. So let us start with vertex 7. So if we remove vertex 7 and given that vertex 6 is already frozen, we need to first freeze all the vertices that are represented by vertex 7, and we also need to freeze all the vertices that represent vertex 7. So first, the first part, we need to hop down to the rows which consist of vertices that are represented by vertex 7. So in this case, vertex 9. We need to freeze vertex 9. So consequently, we'll have to remove vertex 8. Otherwise, again a row will consist of two of its endpoints that are already frozen. But unfortunately in this case we cannot remove vertex 8 because it represents vertex 13, which is not part of the represents table. So there is nothing more to hop around in this case. Now we hop on the top rows or the rows above the second row that we are considering right now, and freeze the vertices that represent vertex 7. So in this case vertex 11, and consequently we might want to remove vertex 10, but unfortunately we cannot remove that because it also represents a vertex, namely vertex 12, that is not part of the represents table. So in this case the number of vertices added, vertex 9 and vertex 11, is greater than the number of vertices removed, which is vertex 7. So this is not a good choice. The hopping around that we did in the table does not diminish the size of the vertex cover, rather it increases the size of vertex cover. So we revert back to our original state, wherein we had made the choice of removing vertex 7. So instead of vertex 7, now what we would want to do is we would want to remove vertex 6. So once vertex 6 is removed, we follow the same procedure. We hop to the row below vertex 6 that consists of a vertex that is represented by vertex 6. So in this case vertex 4 is represented by vertex 6. So we immediately freeze vertex 4, and consequently we also in this case are able to remove vertex 5 because it does not represent any of the vertices that is not in the representation table, or specifically that is not an endpoint in the representation table. Now because we have removed vertex 5, we need to hop below to the row which consists of vertex 0 and freeze it. Now because we are freezing vertex 0, we consequently remove vertex 1. And because we have removed vertex 1, we need to hop to the row that consists of the vertex that is represented by vertex 1. In this case, we hop to the last row. It consists of vertex 3 that is already frozen, and the vertex 2 that is on the same row is not frozen. So this is where we will stop this particular iteration of hopping down. Now we need to hop up, and fortunately in this case there are no vertices that represent vertex 6, so there is no need to hop up. So eventually we stop this hopping process, and in this instance the number of vertices added, that is 2, is less than the number of vertices removed, that is 3. So we have diminished the size of the vertex cover, and now the vertex cover that we have consists of 6 vertices only, and we know for sure that there is no way we can reduce the size of a vertex cover below 6. So this is indeed our minimum size vertex cover that is derivable from this representation table. So this is basically what I meant by the lemma that I had shared earlier, and that lemma in conjunction with another lemma that is already proposed in the preprint that I had shared earlier, we will definitely get the minimum size vertex cover. However, there is some work that needs to be done for diminishing hops. We need to show that it always terminates, it does not kind of get stuck in infinite loops when it encounters cycles, and most importantly, because the number of vertices or the vertex degree of the graph is at most 3, we will be showing that the number of hops is bounded by a polynomial, which is one of the most important things about diminishing hops. Thank you so much.